Good day guys, welcome back to another amazing moment of Wiki Science Tutors. In this video, I'll put you guys through isomerism, which is another wonderful topic to cover in organic chemistry. So as usual guys, let's get started. What is isomerism? Isomerism can be defined as the occurrence of organic compounds with the same molecular formula but different structural formula. Meaning that I can have an organic compound with this molecular formula of C2H6O, but can exist in two different forms when it is expressed in a structural formula. So as a result of that now, we can basically classify isomerism into two different categories. The first one there is that isomerism can be classified into structural isomerism and we as well have stereoisomerism. There are two conditions under which isomerism occur. The first one is that it can either be due to difference in the arrangement of atoms or it is due to difference in the spatial orientation. So when it is due to difference in the arrangement of atoms, we call it structural isomerism. When it is due to difference in spatial orientation, we call it stereoisomerism. So this one is due to difference arrangement of atoms, and this one can be due to different spatial orientation. So in this case now, we can further divide the structural isomerism into four different types. We can further divide them into four different types. The first one is what referred to as the chain length isomerism. And this one occurs when the length of chain is increased. So in this case now, chains are converted into branches. So we can have something like C, 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 which contain 5 different carbon atoms, and you have arrangement of hydrogen around it. In this case now, we call this pentane. Because it contains 5 carbon and only a single bond is present here. But because this chain length is 5, we can change it into branches. Then we can have C, 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 and we have H, 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 and here we have CH3. We can as well have CH3. In this case, this chain length also contains 5 carbons, but when you look at the type of chain this one forms is ordinarily pentane, but the type of chain formed here is position 2, 2, then we have it to be dimethyl, and we have it to be propane, meaning that the chain length has been converted into branches in which the methyl group is occurring now as substituent. However, they both contain 5 carbon atoms and they have 12 hydrogen each. Now let's move to another type of structural isomerism. We can also have referred to as position isomerism. Now the position isomerism occur when the position of substituent is changed. In this case now, we can have something like C, 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 in which you have 3 carbon, you have Cl, you have it to be H, 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 here you have H, and here you have H. Also, what do we call this? We call this 2-chloro. And what is the chain length? The chain length is 3, so we call it propane. However, the position of this substituent called chlorine can be changed. When it is changed, it can be put forward to be C, 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 and here instead of having it to be on the second carbon, it can be on the first carbon, Cl, and here you have it to be H, 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 H. In this case now, the position of that substituent has been changed. And as a result of that, we will not call this one 2-chloro, we call it 1-chloropropane. 1-chloropropane. So in this case now, when you look at this structure carefully, it contains C3H7Cl. This also contains C3H7Cl. But the arrangement of this atom is quite different. Now we move to the next one, which we refer to as functional group isomerism. Earlier I said that you can have something like C2H6O occurring in two different forms. Yes, it can occur in two different forms here, in which you can have C, and here you have OH. Here you have H. You also have H here. You can also have H. When you look at this compound carefully, you realize that it contains 2 carbon, 6 hydrogen, and 1 oxygen. But when you take it in another way around, you can have it to be like this, in which you have it to be H. So what has occurred here is that the functional group here is OH. The functional group here is OH, but the functional group here is O. So as a result of that, the property of this is quite different from the property of this compound. However, they both contain the same molecular formula. So therefore, we'll call this one ethanol, and we'll call this one methoxylmethane. So in this case now, the functional group here is OH, the functional group here is O. So we'll call it functional group isomerism. The last one which we are going to consider is called Tautomerizing. When it comes to the case of Tautomerizing is the scrambling of bond due to high affinity to pi electrode. So let me quickly show you an example of this. In this case, we're going to use a benzene ring. So here we have something like this. Now in this benzene ring, it contains pi bonds, which is formed by pi electrons. It contains pi bonds. And in this case now, we can take a benzene derivative. For instance now, we can take phenol. So this is called phenol. It's called phenol because it contains the hydroxyl group. So when you look at this, the oxygen that is denoted here, oxygen does have high affinity for this pi electron. So in this case now, the oxygen will take up the pi electron to form a double bond. So it means that oxygen has high affinity for double bond. In this case now, we then have a structure like this. We have a structure like this in which one pi bond is scrambled. So we have this pi bond to be present. This pi bond is still present, but the pi bond that is here is now taken to be with oxygen. When oxygen takes up this pi bond, it will have to release this hydrogen because it becomes supersaturated when it contains hydrogen. So in this case now, what we have to do is that it's going to lose this hydrogen in order to become fully saturated and not supersaturated. So the hydrogen will come here. We have one hydrogen here. The hydrogen atom is transferred to this carbon, that which the pi bond is removed. So in this case, we call this one phenol, and we call this one 2,4-diene-hexol. 2,4-diene-hexol. Here, the functional group is carbonyl group, which is C-double-bond-O. The functional group here is OH. However, in this case now, there is scrambling of bond in this case. That's the reason it's not called a functional group isomerism. In the case of functional group isomerism, there is no scrambling of bond. So now, this is everything which you need to know about the structural isomerism. So for instance now, if in a wire question you are asked to draw the isomers of butene, in this case now, you can have it to be C. You have 4 carbons for but. Since it's butene, alkene, you have double bond. So you can place your double bond to be here. So here you have it to be H, you have it to be H, You have your H here, you have your H here, you have your H here, you have your H here. Please, I want you to take note that the carbon carrying that double bond will not take the full number of hydrogen atoms. So here you have H, here you also have H. What do you call this? The double bond is on the first carbon atom. We therefore call this one both 1 in. Now, when we change the position of this double bond, we can have it to be C, 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 C. We have 4 carbon already. So we take the double bond to be on the second carbon. Here you have it to be H, you have it to be H, here you have it to be H, here you have it to be H. Remember, the carbon atom carrying the double bond will not take the full number of atoms. So here you have ordinary H, here you have H, you have H, and here you have H. What do you call this? This is called both 2 in. So what type of isomerism is this? This is called a position isomerism. This is called a position isomerism. Let's now move to what we refer to as stereoisomerism. Stereoisomerism. And let's look at everything which you need to know about stereoisomerism. Now, in the concept of stereoisomerism is also divided into 2 major categories. The first one is referred to as the geometric isomerism, and we as well have referred to as the optical isomerism. Now, in case of geometric isomerism, it is usually due to alternation or correspondence of substituents around double bond. I also call this one the cis-trans isomers, or the cis-trans isomerism. Let's quickly take example of this. If it is 6, it means that the arrangement of those substituents is in the same segment. We call it cis. But if it's in alternate segment, we call it trans isomerism. You can have something like C, here you have double bond. Don't forget, it is always around the double bond. So if I have something like CH3 to be here, I have H to be here, I have H to be here, and I also have CH3 to be here. In this case now, I'll call this one cis. Cis, we have it to be both 2 in. I have C, C. Don't forget, it's always arranged around double bond. So if I have something like H here, and I have Cl here, and I have H here, and I as well have Cl here. Because these Cl, they are in the same segment. When you divide it like this, they are in the same segment. They fall in the same segment. We'll call this cis isomer. This is cis isomer. And what type of isomer is this? We have it to be 1,2-dichloroethene. 1,2-dichloroethene. But when you take it in the other way around, in which you have it to be cis C, and here you have your hydrogen, as well here you have your chlorine, and here you have chlorine, and here you have it to be hydrogen. In this case now, when this particular compound is split into 2 segments like this, you realize that one is in one segment and the other chlorine is in the other segment. We call this trans. So this is a trans isomer. We call this one trans 1,2, the same dichloroethene. Now, let me tell you that the properties of these 2 compounds is not exactly the same. They vary in property, mostly in physical property. They vary in their physical property. Let's talk about optical isomerism. Optical isomerism is usually exhibited by compounds that are optically active. And before a compound can be optically active, it must have a chiral center. What do we mean by chiral center? A chiral center is a center carbon with different arrangement of atoms around it. So when I have a case whereby you have something like, I'll give you 2 examples here. You have C, I have COOH, and here what do you have? You have H. Here you have it to be, that is N2H, and here you have it to be H. As in case of glycine, this is glycine now. Now the atoms or group of atoms arranged around this center carbon, they are not all different. Though this one is different from this, but when you look at this hydrogen here, it means that it is not optically active. active. So I can say that it is optically inactive. Optically inactive. But we can take the case when we talk about that is alanine now. In case of alanine, we can take H, you have C, here you have COOH, here you have N, you have 2, you have H, and here you have to be CH3. In this case now, this is said to be optically active in the sense that the atom you have here is different from the atom you have here, and it's different from the atom you have here, as well different from the atom you have here. So this is a chiral center. This is what I mean by a chiral center. So compounds that have chiral center, they exhibit optical isomerism. When we talk about optical isomerism is talking about the direction of rotation of compound when incidented towards light. And those compounds that rotate towards the left, when they rotate towards the left, we call them level. These ones can either be level, or those that rotate towards the right. When they rotate towards the right, we call them dextro. So in this case now, most amino acids, they are said to level amino acid. And what type of amino acid is this? This is alanine. But in some other cases, they can also exist as dextro. When they exist as dextro, meaning that they will rotate towards right with respect to light. In this case now, we can have structure like we have COOH, and here you have your chiral center carbon, you have NH2, and here you also have H, and you have CH3. We don't call this one level alanine. Instead, we call this one the dextroalanine. We call this dextroalanine. The dextro here means it rotates towards right. The level here means it rotates towards the left. Now, the ability of this compound to exist in two states, in which you have it as right and also as left, we call it mirror image. And compounds that are optically active that exhibit this property are called enantiomers. They are called enantiomers. But compounds that cannot exhibit this mirror image property are now called diastereomers. They are called diastereomers. Also, what I want you to know is that you can have a mixture in which these two compounds are present. Two different compounds are present, and you have them in equal percentage, like you have them in 50%, and as well you have 50% of this. When you have the equimolar concentration of these two different compounds, we call this mixture a racemic mixture. So I believe that at this point, you are able to identify different isomers of organic compounds when you come across them. We have come to the end of this video, and I believe that this video has been really so much helpful in identifying the isomers of organic compounds. Ensure you do well to share this video with your friend, and also subscribe to the channel if you haven't. Thank you for watching this video to the end. We'll see you next time.